What's missing from 100 years prediction on modern binders? The special case of a chloride diffusion coefficient. Welcome to this Rock and Talk seminar. My name is Fabien Georget. The work I'm going to present to you today has been done with collaborators of RWTH, EPFL, and the University de Sherbrooke. So, what's missing from 100 years prediction on modern binders? My answer is nothing. Well, maybe except that. How can I say such a thing? There are many researchers still working on models for chloride ingress. My answer to this is we need to specify the question. For example, we know that there is a very good tool for predicting or at least extrapolating data from 2 years up to 20 years that works on real site exposure. This tool is the apparent diffusion coefficient, or the square root law. It's enough at first order, especially considering field variability. And most of the time, monitoring your concrete for cracks is way more important. I would like to develop these themes into this talk. I will try to explain to you what's in a diffusion coefficient in 3 different parts. First, I would like to say that most of the time, the apparent diffusion coefficient is acceptable. But the real diffusion coefficient is not always that real. And I would like to open this talk by talking about what type of models would really be needed to get a real diffusion coefficient. So, as I said, the main question is trying to first ask the real questions. In this talk, in particular, I will focus on this particular question. Suppose that I want to make a new bridge next to the sea. The question I have to ask is, which environmental friendly binder should I choose for a good resistance to chloride? To do this experimentally, we know how to do. We put a sample in contact with a model of seawater. After a while, the chloride is going to ingress, and after a while, we're going to be able to determine the total chloride concentration as a function of depth. These are often the different curves that you can see in the literature. This is one example that shows different binders: OPC, calcine clay, slag system, and fly ash system. As you can see, every binders behave very differently. Currently, in most models, there are 2 ways to explain it: through the porosity and the chloride binding. However, if you look in this publication for the details, you will see that none of these parameters can explain these variabilities. Instead, we see that this apparent diffusion coefficient is way better correlated to the alkalinity in the 28-day pore solution, which is related to the conductivity of the pore solution. So how can we get a better understanding of the real differences between these binders? My first point here, and my first assumption, will be that binding is important, but not that crucial. So I will forget about it. This talk is going to focus on the effective diffusion coefficient. And the reason is quite simple, is that if you look at the diffusion coefficient, you can see several, at least 1 order of magnitude difference between the most diffusive and the least diffusive systems. While if you look at the binding capacity, the differences between the system is not that big. So to focus on first order, we can only focus on the effective diffusion coefficient. We'll be happy to talk about chloride binding, and I've done some work on it. You should not forget about it, but it's not the focus on this talk. So because we focus on diffusion coefficient, we have to first define what is a diffusion coefficient. Probably at school, you started it with a fixed law. This is a good way, but I much prefer the way I'm going to present to you today. This way is based on thermodynamics of irreversible systems. This seems quite awful and mathematical, but won't worry, it is very simple. The Osage reciprocal relation states the following. If you have a driving factor, for example, a gradient of concentration or a gradient of temperature, this will induce a flux of ions, a flux of heat. And in between, you have a coefficient of proportionality that you call the transport parameter. If we apply this law to diffusion, we get the following law, which is very close to the fixed law. In this case, the diffusion coefficient is not a special parameter. Is it a thermodynamic parameter that is a coefficient of proportionality between the driving factor and our flux? This is very useful because it allows us to define diffusion coefficients for many different aspects. For example, if you have no driving factor, then you call this the self-diffusion coefficient. If your concentration are very low towards zero, you call it the limiting diffusion coefficient. These are the values that are usually tabulated. And if you're looking in bulk water, then you call it the molecular diffusion coefficient. This corresponds to a gradient concentration between two parts of your bowl of water. Now, if you're talking about a macroscopic cement sample, you don't have to consider only the liquid phase. You need to consider both the solid phase and the liquid phase within the pores. So we call this one the effective diffusion coefficient. It corresponds to a macroscopic average concentration. And there is an associated gradient of concentration between the two sides of your samples. But this is only one way to define this effective diffusion coefficient. You could also consider the non-ideality of your pore solution. And in this case, you would have to add a term describing the non-ideality of this solution. But if you consider a complex pore solution, then you also need to consider the effects of the other ions. And you need to go towards a more complex equation. For example, here is the Nernst-Planck equation, considering the diffusion in ideal condition, the correction from the non-ideality, and finally, the coupling terms due to the effect of the other ions or the extra potential that can be added to the system. So this is very nice. We have a nice way to define diffusion coefficients in different systems. But you give these nice tools to cement scientists, and the first thing they do, they break it. We saw that these things looks vaguely like a diffusion profile. If it looks vaguely like a diffusion profile, let's try to define a diffusion coefficient according to it. This coefficient diffusion is called the apparent diffusion coefficient. But as you can see, in this case, the gradient factor has to be the total chloride content, because this is what is the most easy to measure. But the total chloride content contains both mobile species, the chloride in the solution, and immobile species, the chloride that is bound to the system, to the solid phases. So this gradient is not really a good driving factor because some of these elements cannot move. So how can we use this system? How does it even work? Well, the answer is much simpler than it seems. It's that sometimes you can prove even that it should work. For example, if we have linear binding isotherm for chloride binding on solid phases, then you can prove mathematically that your apparent diffusion coefficient has to be related by the diffusion coefficient as related in this equation. You can find all the data in the papers, in the preprint that you can find on ResearchGate. Linear binding isotherms seems a bit far-stretched, but in fact, there are many ways to construct them by considering a pH-dependent binding isotherms. Whether it is true or not needs to be limited, but it is important to notice that there are ways to define properly the apparent diffusion coefficient and still have a meaningful way to use it. It is not a parameter. It is not a nonsensical parameter. And in fact, chloride ingress is governed by diffusion. We know that chloride ingress is governed by diffusion. And a process governed by diffusion has to respect the square root law. If you are still scared with the apparent diffusion coefficient, you will prefer this approach, although they can be proved to be equivalent. The square root law states that for a process governed by diffusion, the depth or a certain distance is proportional to the square root of time. This is illustrated on this set of process where we have a concentration related to the depth, which when we plot in terms of this spatial variable, x over square root of time, merge into a master curve. In carbonation studies, we're mostly used to see this as this relation in this graph where the depth of penetration is plotted as the square root of time. But they are equivalent view of the same thing. And this can be very well applied to the chloride ingress case. To demonstrate it, we can show again a different set of concrete site. And as you can see, if we plot this profile obtained on real concrete, you can see that they all merge towards a master curve, especially after 2 years. It means that you can really define an equivalent diffusivity of the system. And this equivalent diffusivity is sufficient to capture most variations of your system. And you could say, yes, it is not perfect, but have you ever tried to do experiments of concrete? They are never going to be perfect. We have captured the first order variability in these experiments. And this is true at this very late stage, but you can even apply these experiments at early stage. For example, we use the experimental data from this publication that goes from 1 day to 180 days of exposure. And you can see that you can define an equivalent diffusivity. You could say that, oh, there is a big difference at the end of the curve. Yes, but you should focus on where there is no difference, where it is meaningful to define this diffusivity. And this is the main pictures I would like you to keep in mind, that when you look at this chloride content profile, what is important is the center of the curve. Yes, we know that at the surface, we are going to have a lot of surface effects, for example, due to leaching. And at the bottom of the curve, we are going to have other effects due to the dynamic microstructure. But if we focus on the center of the curve, we can characterize the main diffusion behavior of our binder, which is sufficient in a first order to classify the different binders that we can choose for special application. And is it sufficient? Yes, it is sufficient. This is a set of data that I can show you from that has been obtained on OPC and a limestone calcined clay cement. And as you can see, in this simulation, not only we can see that there are many different diffusivity between the system, but even in the for the same system, but different water to semen ratio, we can obtain meaningful differences. So this equivalent diffusivity can tell us a lot about the intrinsic behavior of our system. And as a conclusion for this part, I would like to say that this apparent diffusion coefficient is not that bad because it characterizes the overall chloride ingress, and it can be used as a tool to extrapolate at late age, and more especially trying to analyze changing in the materials between what you thought was at the beginning and later when you do the extrapolation. So this equivalent diffusivity may be not a very predictive tool, but it's a very useful tool and a very useful tool and a good support for monitoring of structure, as it allows you to detect deviation compared to the expected behavior. And I would like to emphasize more that this equivalent diffusivity is intrinsic to the diffusion process. And chloride ingress is a diffusion process. So it will always be possible to find an equivalent diffusivity, even if your model is wrong. So even if you think you're fitting the true effective diffusion coefficient and diffusion profile, you never get much better than this apparent diffusion coefficient, irrespective of the model that you use, because there are many parts of the models, for example, the chloride banding, that are very uncertain also. So let's go back to the definition. We have this flux, which is the Nernst-Planck equation for the flux. There are three different terms: the ideal diffusion, the non-ideal diffusion, and the extra term that is added in the Nernst-Planck equation that correspond to a diffusion due to a gradient of potential. It means that if we can neglect the diffusion, we could measure the diffusion coefficient just by looking at this term, which is not a true diffusion. First interesting observation. The second interesting observation is the meaning of this potential. This potential has nothing to do with CSH surfaces. This potential should be seen as two different things. Either it corresponds to an applied electrical current, or it is an electron neutrality correction. All the CSH surfaces effect have to be added to this diffusion coefficient, because this term is a macroscopic term, because we want the effective diffusion coefficient, which is the macroscopic diffusion coefficient. So let's take this idea of measuring the diffusion coefficient without diffusion. This is, for example, the mean migration, but this is also used in many tests, including standard tests that use electrical potential to drive a migration flux of chloride inside the sample. This often looks like this, where you have a sample in between two reservoirs, a reservoir rich in chloride and a reservoir poor in chloride, and you apply a potential such that the chloride moves through the sample. And you can measure current or concentrations. In this special case, this is the current, the concentration that are measured, and more specifically, the flux. Because we know the flux, we know the potential, we can predict the diffusion coefficient. And this is, for example, some results that we obtain on many different binders. Of course, this is an experiment, but we can make it a model too. This is one example of such models that can work for it. It seems very complicated, and it is quite complicated, in fact. but we can make it simple. You can recognize the first term as being the ideal diffusion, the second term of the flux as being the non-ideal diffusion, and the final part, the Nernst-Planck term due to the migration of electrons. I would be happy to discuss more details, but this is not the point of this talk. Let's just assume that this model works. This is the type of results that we can obtain. At 0, we have the reservoir reaching chloride, so chloride concentration of 0.5, and at 3 centimeters, we have the reservoir pouring chloride. As you can see, we varied the initial hydroxide concentration in the pore solution. This is an experiment, so we can do it very easily. And as you can see, when we increase the initial hydroxide concentration, we're going to increase the concentration that is in the sample during the migration experiment. This can be easily explained by the fact that chloride is not going to simply move into the system, but electron neutrality still have to be respected. So chloride is only going to replace some of the hydroxide. The more hydroxide you have, the higher the concentration you can go through your sample. But if you look at the equation that we have a special concentration term in this equation. So which concentration should we use? Should we use the concentration in the upstream reservoir, or should we use the concentration in the sample? Well, this is a simulation, so I can do both easily. In red, you have what I call the model diffusion coefficient that is only easily obtainable with the model using the simulated concentration. In blue, you have the effective diffusion coefficient, the measured diffusion coefficient, which consider fixed concentration. These values are modeled to the input diffusion coefficient, which correspond to 1. And as you can see, they are quite different to what we expect. We would expect that since the input diffusion coefficient is equal, is always the same in all this simulation, the measured diffusion coefficient should always be the same. This is clearly not the case. And our diffusion coefficient is function of our initial alkali concentration. It means that this effective diffusion coefficient that we measure is not an effective diffusion coefficient. It is more apparent to an apparent diffusion coefficient. Is it a problem? No. And in fact, this is related to our first point. It has been shown in many publications that, and reviewed in this review paper, that in fact the apparent diffusion coefficient is often or very well correlated to the diffusivity, to the conductivity of your sample. And this was verified in our mean migration study that what we measure is a function of the bulk conductivity. It means that the diffusion coefficient that we measure by the mean migration method might not be the effective diffusion coefficient, but in some way it is more useful than the true diffusion coefficient because it is directly related to the apparent diffusion coefficient, which gives us a direct indicator of the performance of a specific binder. So using this measure, we can get a very good idea of which system will perform very well in a given environment. Should we focus on this relation between the diffusion effective and the conductivity? Yes and no. It is very good to have this relation, but it is not unexpected. In fact, there is one fundamental relation between the diffusion and the mobility, which is given by Einstein's relation. The mobility is related to the conductivity. The conductivity, sigma, is the mobility times the concentration of charge carried. As a relation, then we expect our diffusion coefficient to be well related to conductivity, whether you only consider diffusion coefficient or you try to create formation factor experiments, for example. But of these terms, diffusion coefficient, formation factor, apparent diffusion coefficient, conductivity, they are all explaining themselves the same way. They are related to each other. So we cannot explain diffusion coefficient because of conductivity. Rather, we should see each of them as a classification parameter. And it is a very good option because it means that just by measuring the bug conductivity, we can get a very, very good estimation of the resistance to chloride ingress. So yes, we don't need much more to predict 100 years plus performance of chloride ingress, because we can measure the conductivity at very early age and try to classify which systems are going to be good, and more specifically, compare them to systems that we know works. If your conductivity is lower than a system that you know works, there is a very good chance that your new system is going to be good enough. Of course, this might be a bit disappointing from the modeling side of view. So I would like to spend the last part of this presentation to go a bit further. Can we make a predictive model? And yes, in some way, we know the way towards this predictive model. For example, assuming that we have this flux equation, then we can define a diffusion coefficient as a combination of different factors: the limiting self-diffusion coefficient, the percolation path, the effect of solutions, and the interaction with surfaces. Of course, if you consider different type of equation, then you need to be careful to change your model. For example, the effect of solutions, such as ion competitions, are now taken care by these terms and do not need to be taken explicitly into account in the effective diffusion coefficient. We can look at all these different terms and try to make some kind of understanding. For example, we can compute the effect of solution composition on self-diffusion coefficient. As a rule of thumb, it is not that important, and we can expect variation up to 10%. We can also try to estimate the effect of the surfaces and transport in nanopores. Yes, many effects can be observed or modeled, but they depend a lot on the CSH surface model. So the first thing we need to do is to better understand what are CSH and what is the geometry of these pores. Because, of course, geometrical effects are still going to be important. They are not the only important, but we know that they are there. But the main challenge is really to characterize the pore network in a geometrically meaningful way. The tortuosity at its use currently is quite not enough to get a good idea of what's happening in our material. So I would like to conclude this talk by saying that the apparent diffusion coefficient most of the time is acceptable, especially if fitting is involved. Then you know it is a fitting parameter describing the diffusion process of your system. It is also always important to define your diffusion coefficient with the corresponding flux equation. Finally, conductivity is useful as a classification and not as an explanation. And if you fit D, then it's an apparent, you should consider it as an apparent diffusion coefficient. You should not abandon it, but you should consider the limitation and advantages of the approach. If you want to go towards a more meaningful physical question, then the main question you want to go to answer for a correct quantitative model is to know what's a CSA gel force. Once we know what's a CSA gel force, then we can accurately model the surface, and we can accurately model the effect of the geometry and try to make more predictive model. Thank you very much for your attention.